Okay, so welcome everyone. So this is lecture 7, and some logistics is uh, we have the mini project that's been released, and hopefully you guys have already started working on it. The part 1 is due, I think it's coming Saturday. Urvashi is not here, but I believe it's coming Saturday. And part 2 will be released tomorrow, and it'll be due the next Friday, the following Friday. So it's just staggered that way, so you don't have, you're not like crammed on time, and you're able to space it out. But part 2 is connected to part 1, so all the parts are connected, so there's a continuation of content. So do make use of Discord and office hours. I see the Discord is very quiet, so feel free to share your thoughts or ask questions or have a discussion going there. It's not just us making announcements or sharing information. You can also share information. It's your Discord channel, so feel free to use it more, and feel free to pick up any discussion you want to have there. Are people able to attend office hours? Anyone's been to office hours? Okay, one of you. How about others? No. So feel free to leverage the office hours. We have you've been to office hours.
No, we just got a question for that project. The mini project, is that mini project group project or?
Mini project is a group project. Haven't we set it up that way?
I'm not sure. Urvashi was the one who set it up.
Okay. Let me talk to Urvashi. So it's ideally a mini project. At least your 2 and 3 are going to definitely be mini projects, group team projects. Mini project 1, I think I'll just talk to her and see if we need to make it a team project or not. But 2 and 3 are going to be team projects. Okay. If you already started working on it, continue, no issues. If there's any changes, we'll let you know if it has to be a team or not. Okay. Yeah, so do leverage your office hours. We have a couple of office hours. And I also stay back after class, so if you have any questions after class today, you can come up and we can discuss. And how many of us have been to review sessions that happen on Friday? Okay, I see a few hands going up. So feel free to leverage that as well, because it's a nice recap of what's happened in the week. So
Did a recording of the review session?
Did we have a recording?
We did not record it this time.
Oh, okay.
Yeah.
So let's
I'll
record.
make sure to do it next time.
Yeah. I think we have a recording of the first one, which I think the first review session that happened with the Urvashi. The second one's not recorded, but we have the slides for it, right?
Yeah, I can share it.
Okay, so we have slides for it that we can review. Yeah, so we'll record every review session, and then we'll share. The TAs will share it on the Discord. Okay. All right. So paper presentation, I think we had a good start last lecture with paper presentation, but there's some, I would say friendly guidelines for you guys to get the most out of your presentations, and also others who are participants or who are like listening to you, also for them. Let me just make sure, let me restart. So today's lecture is on multi-head attention. There's some deep learning references and embedding references and attention references I've shared here. There are many other references that you can look at, but these are a few connected to what we are covering in the lecture so far. So we said that the fundamental transformer architecture has an encoder and a decoder, and BERT is kind of based on this, and then GPT is based on this, and then you also have models that like BART that look at both. So, but yeah, these days people mostly look at just encoder based architectures or decoder based architectures, but people have also explored the combination, and that's where you have encoder, decoder, attention. So this line that goes between the encoder and decoder, that's like attention between encoder and decoder. We looked at an example, but last lecture, let's go through it again anyway, just to understand the flow of how you go from words to tokens to weights to transformations to like the final output, right? So let's say you have a raw input sentence, I love machine learning, and at this stage it's just a string, there's no math. Uh, and then some text normalization happens. And this is just at the language level. We've still not gone into tokens. You might want to lowercase words, might want to do Unicode normalization, clean up any extra white space. Sometimes documents come with tons of white space and stuff. So kind of normalize it. Just reduce any unnecessary or redundant characters in the documents, right? Then you apply some kind of a tokenization. So we discussed that every LLM has a tokenizer that's connected to it. So it kind of comes with a tokenizer. And so let's say we are looking at word piece tokenizer, which is used by BERT. It breaks words into subword units, and then you generate tokens for those. So for example, unhappiness gets broken into happy and #ness. So yeah, call this prefix continuation pieces. Then we add some special tokens as well once we've broken it down. So let's say this is already broken down. If not, you kind of break it down. May #chine. I don't know. Chine may not make so much sense. Yeah, but yeah, this will make sense. So #ning, because you see that a lot. Okay, so you might have some breakdown of these, and then add a start token and a separator or end token as well to separate the sentences, right? So this is all happening at the word level. We're still in the word space. Now we convert them into token IDs, because everything can be mapped to a token ID once you tokenize it. There'll be no such token that you're like, I don't know what the token ID for this is, because you've already mapped it out. So you'll always be able to map. If it's an unknown word or some unknown character, you'll map it to an unknown token. There'll be an unknown token ID, right? I've never seen this before. Just map it to an unknown token ID. And then you'd have had training examples where you have to deal with that. Or it can be deliberately inserted to say that, hey, somehow break it down into this unknown token. But so convert all the word pieces into token IDs. So that's the next step. So this is the CLS, this is separator, and these are the other word pieces. So now that we've tokenized it, or we have token IDs, we've kind of understood where to start, what the starting point is. So once we get the token IDs, we get a token embedding, but that's not the final input embedding. The final input embedding starts with the token embedding, but you also need to encode position, and you also need to encode segment ID if needed, right? So token embeddings are already learned. Like every token ID is connected to a token embedding. So that's already learned during training. It comes for free. So if you say, okay, token ID is phi, then it comes with a specific vector. It's already learned. So it's just a hash map between token ID and the token embedding. So that's already there. It's not random, it's learned from data, right? Or you just set it up and then train it, and then the training pipeline helps you learn those embeddings, right? So this is a learned vector ahead of time. Then we have position embedding, which encodes a position or token order. We looked at an example of chocolate milk, milk chocolate, which have different meanings, but they have the same set of words. So unless you have an encoding of sequence information, you're not able to differentiate the different kinds of combinations of words you can have, and consequently there are different meanings. You're not able to differentiate it without a proper positional encoding. So that's something that happens with position embeddings, and these are also learned for every single position. So, and the number of positions it's learned for is what is the number of how many positions do you go until for a given large language model? That's the embedding dimension of a token. But how many such positions do I need to learn the position embedding for a given language model? How do I know when to stop? So that's decided by what's called the context length. So every large language model has a maximum context length. It says, okay, I can support, it used to be that you could only support 4,000 tokens. Now they can support 128,000 tokens or 256,000 tokens. So you learn position IDs for so many, but not more than that, because you'll not be able to fit it anyway. You'll discard it, right? So anything more than that, you just discard. Say, I can't handle it in context, so we'll just discard the rest. So you learn as many position embeddings as is the limit of your large language model, right? And you have it stored. That's also stored somewhere. And yeah, so now that we know the position embedding, we also include that and add it to the token embedding. Yeah.
When you say position embedding, what do you mean? Like, your example.
Yeah.
Saying CLS.
So let's say I love machine learning, CLS, and separator. Okay. Let's say these are already subwords, although they're full words. Let's say they're subwords. So this is position 0. This is 1. This is 2. This is 3. This is 4. This is 5. Now let's say I continue the sentence with saying machine learning, blah, blah, blah. The next sentence. So this is position 6, position 7, and so on. So if you look at the token embedding for this is token embedding of machine plus position embedding of 3. This is token embedding of machine plus position embedding of 6, right? Because it's in the 6th, the index is at 6th position.
But what is the learned part of the position?
So you learn the embedding itself. So the position embedding is fixed, but it's learned. If you say position 6, it's always going to be this embedding.
So it's not the 6, it's some.
No. So
Some
yeah. Absolutely. So if you look at an embedding, right? Embedding is always in some dimension, like 768 or 1500 or something. So there'll be a numerical vector with floats of so many dimensions. So always think of an embedding as like a 1,000 dimensional vector. So when we say position embedding, it's a 1,000 dimensional vector of floats. So for position 6, it's always going to be a particular vector. For position 7, it's going to be different. But how do you know what those numbers are? That's learned through the training of that large language model.
What is it learning in that word? Like position itself can be for the same letter can show up a statement word can show
Yeah.
up in.
So the learning happens at a very high level. You say, okay, we'll get to this. So there are learning objectives for every large language model. So one learning objective is predict the next token. Okay. So if you want to predict the next token, let's say I say I love chocolate, the next token should be milk, right? Or it could be something else, right? It depends on what you see in the document. If you say I love milk, the next token can be anything else. It can be chocolate, it can be something else, right? So I need to differentiate that the chocolate in this position is different from the chocolate in that position. But that's something for the large language model to do, and it has the framework to learn it in that way. So across all possible words for which I predict the next token, right? And also I predict missing tokens. So that's the masked language model where you say, here's a full sentence, predict the missing token. So I pass in like millions and billions of data. Across those billions of data, it says that these position encodings help me learn the best. So it's not for any particular sentence.
Yeah, I get the fact that relative
Yeah.
positioning is important.
Yes.
But what is the what are you going to learn about position 6's encoding is this and position 7's
Yeah.
encoding is this, because the same letter or same word could show up on
Yeah.
any position.
Correct. So it's more that when you add up these vectors, the model is able to understand that somewhere this is position 6. It's able to differentiate it and treat it in a different way than if it was at position 1 or position 10, right? It's not necessarily that it's a relative thing, like you said. Inherently, position 6 may or may not have much meaning, but it has to be different from position 7, and it has to be different from position 5. If position 6 and 7 had the exact same vectors for position encoding, there would be a problem, because then I'm not able to differentiate. So it will definitely learn something that's differentiated, and it might also learn something about the semantics of language and how it begins. So if I always start with I or whatever, so I might end with certain words, then those positions matter to me as well. So there are certain things that start in the beginning, there are certain words that end in the, at the end of the sentence, and there's some things we find in the middle, right? Or the second word might always be some verb or, a different kind of, so there are statistics around it that also it'll learn and encode into the position embedding. Yeah.
So positional embedding are unique vectors assigned to each position.
Yes.
Fine.
And learned.
Yeah. What defines context length?
What defines?
Context length.
Context length is defined by.
What determines context length?
Context length for a particular language model is decided by those who design that language model. So like, GPT will say, okay, we are able to do 8,000 tokens. That's the maximum context length. So then Meta will say, okay, I'm going to release a model 2 with 8,000 tokens. And then so people want to increase the context length because the more documents you can fit in context, the better, and I can do better on that. It's a good thing, right? So I always want to keep increasing context if I can.
How do they decide on the context length, given context? Why it is 4K for one model?
Because there are applications that you notice will probably require 100,000 tokens, and you're simply not able to handle with 10,000 tokens. So the business context and the need decides that you are looking at. Like there's a separate body of research for large context generative AI. That's a whole thing, and recursive language models is one take at handling large context, right? Yeah.
I just wanted to add something to the first question regarding the positional embeddings. What you were saying is exactly right, is that the relative position difference is much more important than the absolute position. In other words, if we have like two words that are at position I and J, if we just translated and shifted into a later position, the degree to which they attend to each other should be preserved. But that's actually a flaw with this approach that was fixed in much later papers. So this one has the problem that it encodes absolute position, but yeah, the later ones actually don't learn position embeddings, and it's something that you kind of hard code so that it only encodes, or it's only a function of I minus J, where I and J are the locations in the sequence. But this is like one of the early times.
Yeah.
So for the token vector, like, how do you determine the split into subwords and how many subwords are generated? And also, how do you determine the length of the embedding vector?
Oh, length of the embedding vector. Okay, so length of the embedding vector is easy. So you start increasing the length of the embedding vector, and you start seeing diminishing returns at some point. So then you say, okay, this is a good one, you can stop here. Or you want that extra 5% improvement. Like if, for example, you look at BERT base, one of the first models, that's like 768. And then BERT large is double that, right? But it's not that you're going to get twice the improvement if you went from 768 to, whatever the 15, what is the, twice that number, 1536, yeah. So if you went from 768 to 1536, it's not like you're going to get twice the accuracy improvement. You're going to get a marginal improvement, right? But it's also going to take up more memory and more training time and more inference time. So it's also a trade-off between latency, memory, accuracy. But you don't want to train with 10 dimensional embeddings. You're going to get nothing. So there's a minimum number for which you are able to actually get some reasonable predictions, right? And also people also break it down, the benchmarks, by the number of parameters of the model. So if I have a large language model, I'm going to be obviously looking at large, everything is large. The number of layers is large, the embedding size is large enough. Small language models, you only compare within that realm, right? You're going to compare one small language model with something else. So they'll have kind of similar dimensions, but they'll be lower than a large language model. And their benchmark accuracies will also be lower. So, but you're operating in that space. So to operate in this particular space where you get a specific accuracy, what's the minimum amount of hidden dimensions you need is something we experiment with and we learn. So definitely 100 dimensions is too low. But 2000 might be too high or not needed. You can make do with 1500. So that's experimental studies on how, accuracies change with the number of dimensions. So you can think of it as a hyperparameter too. So you're optimizing for a hyperparameter, and you use whatever hyperparameter optimization techniques are there to optimize for that.
I want to go back to vocabulary. Do we have to use predefined vocabularies? Can we create our own based on the data?
Oh, predefined, yes. So we'll look at, so there are different kinds of encodings. So there's like byte pair encoding. So you encode in bytes. So that's used by some of the language models as well, versus just using words, right? So how many bits of information you have. So we'll probably touch upon it in a separate lecture. But yes, there are different kinds of encodings that are not directly dependent on the given data, right? But having a transformation of it into a different representation space. You have to represent it in some way that they're all differentiated. That's important, right? But so how you represent it, that's depends on the tokenizer. So word-based tokenization is one. Byte pair encoding is another one. Okay. So does that clarify? Context length is set by the language model and the capacity that they use for training. Because if they didn't use, like you say, okay, I want to use more context, why don't you make it work? Well, they cannot, because the architecture is limited to that many tokens. There's just simply no extra weights available to handle extra tokens there. But it can handle fewer tokens. You can handle 1 token, 2 tokens, but as much as the limit of that language model. Right? I think the recent GPT models can handle 256K tokens. So really large context. Not to say that they're going to be accurate over that much data. Their accuracies will also start to drop as you increase the context length for different tasks. Okay, these are good questions. Yeah, so we take the input embedding is a combination of token, position, segment. So you kind of sum it up. And at this point, we're able to take the input embedding and form a matrix because let's say we have a sequence length of 6, and then we have a hidden, so it's called hidden size. You can also say embedding dimension. So BERT base has an embedding dimension of 768. BERT large would have 1536 dimensions as an embedding dimension. Okay. Yeah, so then once we have this input embedding, and we have this input embedding matrix, so this is a matrix of 6 by 768. We'll call it input embedding. So this input embedding matrix captures all the essential information in this whatever representation space that we use based on the tokenizer, and it's just complete, and it's just matrix of floats. The matrix of floats has all the information of the sentence "I love machine learning." So I love machine learning got transformed into 6 by 768 matrix. And this is the matrix that the transformer cares about. That's it. It doesn't care about words anymore. It'll just handle everything based on this matrix of 6 by 768. So that's a representation. You've chosen a representation that's numerical, that's easy to manipulate, work with, transform, do linear algebra, do a whole bunch of activations, and then get an output. Okay. So now with BERT base, it has 12 identical layers. I think BERT large has 24 layers, so it has double the number of layers. So we pass it through all these 12 layers through multi-head self-attention and also through feed-forward neural network. So we'll go into the specifics of it today. We'll go a little bit deeper into it, look at the math today. So today is kind of a important lecture to dive deeper into the transformer architecture itself. After this class will be, like once you've done this, will be more high level, right? Today is like more detail oriented, and we'll actually be looking at the matrices and matrix manipulations and everything today. But that's, once we're done with that, the rest of the lectures will be like high level, and we'll be looking at different concepts. Okay. So yeah, so we passed through 12 identical transformer layers, and this architecture hasn't changed fundamentally, right? The multi-head attention and feed-forward neural network, it's the same. It's stayed the same all the way to 2026. Something that was proposed in 2017 hasn't changed at that level, right? There have been other changes, there have been other developments and improvements, but this idea of having a multi-head attention and a feed-forward neural network hasn't really changed. I think DeepSeek has introduced some new things. So along with multi-head attention, it's like multi-head latent attention, and so ensembling. So there's also like mixture of experts. But those are like new, you can say, modifications, but it's been very recent. Otherwise, we've been sticking to this setup. Okay, so essentially each layer, you have two components. So where's multi-head attention? So yeah, so we have multi-head attention, we have feed-forward neural network, and then we have a residual connection and layer norm. This has flipped. I think recently people have flipped the layer normalization and to be ahead. So that's a little bit of a detail we'll cover when we come to the more recent architecture. But essentially you have multi-head attention, feed-forward neural network, and some normalization. This is more for training, stabilizing the training, and residual connection, so you don't lose context that you had in the previous layer. You continue the context. Because you keep doing matrix vector multiplication, sometimes you can change the structure or information. So the residual connection ensures that there is a continuation of what you learned before. You don't forget what you learned in the previous layer. So you add it up to what you learned now. So it's kind of upgrade the learning versus like completely change the learning, right? So that's the idea of residual connection. Okay, so once we pass through all the 12 layers, we extract the CLS token, and that's 768 dimension or 1536 dimensions. And then we use it for classification, regression, sentence level tasks. So this is something that you also looked at with assignment 2, is training a BERT model based on this. Okay. So now what we'll do is we'll actually go deeper into multi-head attention and feed forward. So today, kind of like dive deep into just one layer. Just look at one layer and just like go through that layer and say what's actually going on between input and output. How does the input get transformed to the output when it just goes through one single layer, right? Okay. So we covered this transformer types, encoder only, encoder, decoder only. All right, so this is high level. Okay, now let's start diving a little bit deeper. So like we said, if you're looking at BERT, we're going to use BERT as an example, but when you switch the architecture, you'll see not too many changes happening. But it's good to start with BERT. BERT was one of the first transformers. So like Llama 3 might be different, but it's not going to be too different. So we can quickly adjust to other architectures as well. So we'll look at BERT. So looking at the encoding layers, right? Like we said earlier, BERT is trained based on next token prediction and also masked language prediction. So you just take a sentence, tokenize it, mask one of the words or a bunch of words, and say, can you predict that accurately? I also predict the ones that were not masked, right? So essentially reproduce yourself, but also fill in the missing tokens, right? That tells BERT that I'm able to understand and interpret language from all directions, like not just the next token, but also something that's missing in between, right? So I'm able to understand language in different ways. So that's the idea of masking. So it's fine-tuned on different objectives. So let's look at one of the layers. So let's say the first layer that looks like this: multi-head attention, layer normalization, feed forward, and the residual connections and stuff. So let's look at this. We'll use an example of thinking machines. Okay, so just 2 words, thinking and machines. How does it go through just one layer? So we'll take a look at that. So we're using BERT base. So embedding dimension is fixed to 768. Let's say there are 2 tokens. If we're not breaking it down, we might actually break down in practice, but let's just assume 2 tokens for now. So let's compute the input embeddings, right? So token embedding, position embedding. Let's say we also have segment embedding. We take each of these and sum it up. So this matrix is the input to layer 0. So we sum it up for each token. So for thinking, I get this token embedding plus position embedding plus segment embedding. And for machines also I do the same. And each of these is 768, right? So that's why this is 2 by 768, because there are 2 of them. So 2 rows, each row is the embedding vector for that token, right? So 2 by 768, this also makes sense. So let's look at an in-class exercise. We'll do a little bit of math through a bunch of in-class exercises today. So feel free to open up your laptop and just pick an answer for this question. So token embedding for thinking is 1, 2. So these are embeddings in 2 dimensions for simplicity, but just to work through the math through hand calculations yourself and be comfortable with manipulations, right? So we're just looking for embedding vector for machines, input embedding vector for machines. All right, so now that we have an input embedding, and it's like 768 dimensions for thinking, and then 768 dimensions for machines. So what BERT does is it actually uses multi-head. So multi-head is you actually break it down into different heads, right? So you have, let's say, 12 heads. Each head has its own set of weight matrices. So you can say each head is like learning a different understanding of the input. It's like maybe one is capturing more of the parts of speech of a sentence. The other is understanding the semantics. The other is kind of connecting relationships between entities. So every head is like having a kind of assigns itself a different task. It says, I'm an expert on this. If you want parts of speech, go to head number 5. If you want to understand, more of the semantics and how the words are related, then go to head number 3. You don't know which head it is, but when you examine the relationships, when you pass a sentence, you'll understand that, oh, looks like head number 3 is more on semantics and head number 5 is on parts of speech. And head number 6 is looking at how they connect to how the consecutive words are connected, right? What are the words that are following each other? So you get heads mapped out to different tasks or goals once you examine the inputs that get passed through it. So it's after the fact. After you've done training, you realize, oh, this is what this head is doing. Okay? Yeah.
What's the difference between having 12 heads and just having a hidden layer that's the same size as those 12 heads?
Yeah, that's the thing. You have 12 different weight matrices versus having just one weight matrix for a given head, right? So when you change the weight matrices, the model gets the freedom and flexibility to learn different ways of transforming the output and different ways of capturing self-attention. So I want to give attention to other words in my sentence, but how am I giving attention is different because the weight matrices are different for each head versus if I had just had one weight matrix. So that's kind of the high-level intuition. Okay, so
The 1 for 12 is again just empirical.
it's like, let's have enough number of heads, but as you have more heads and more layers, and more hidden dimension, the number of parameters starts to multiply. So it's like I think BERT large has 24 layers and then 16 heads. So yeah, it's like you can say it's a construct. Within the construct, obviously, how do you pick these numbers? Well, you see that like if I didn't have any head, there's a problem. I'm not actually making progress. So let's have a few heads. Now, how many heads? Maybe 100 is too many, right? So that's kind of the idea, is like you experiment with it and see what's the sweet spot for the kind of data. Also, it depends on the data. Like if it's a large language model or if it's a small language model, the more data you have, the more you can extract understanding and insights, the more these heads start to matter. But if you're dealing with like less data and you're limited by a small language model, you can only learn so much, so you don't really need so many heads.
And maybe it will come out once we do the thing, but like how is it that the heads learn unique things as opposed to learning the same thing 12 times?
Yeah. So this is the idea of like having deep representations and so many layers and parameters, is you give the model the freedom and flexibility to learn how it wants, but make sure you get to the accuracy has to be high. See, my benchmark is that my loss has to be low, my accuracy has to be high, and I'll give you all kinds of data. If there is enough freedom, if it makes sense logically that it can do these things, then it'll do it. If it doesn't make sense, then it's limited, right? So this is like, for example, if we didn't have, let's say we didn't have self-attention, that's kind of just pure vanilla feed-forward neural networks. It's limited. You can add as many layers as you want, but because self-attention is missing, it's not able to correlate with different words. So now that you introduce self-attention, there is freedom for the model to leverage it. How much it's going to leverage is based on experiments. And it's like let's see what happens, right? But at a design level and at a architecture level, does it make sense, right? And then let's try and see, and then it's it actually happens. So the pieces fit the puzzle. Someone coming. Arnav, you want to share something? You had something to share? Or?
No, I think that's good.
Cool. So because we have 12 heads, you can say that each it's essentially a 768 dimensional vector, but let's break it down across 12 heads. So it's 768 by 12, so 64 dimensions, right? So what will happen is for each head, you learn these query, key, and vector value matrices, right? And query key value is a way to understand how much attention should I place on other tokens for the first token or the second token, right? The query and key tell you how much emphasis I need to place. The value tells you how to add it all up, right? How to combine the understanding, right? So that's where query key value comes in. So like we said, every head has its own set of weight matrices for query, for key, and value. So this is, let's say we look at head, let's look at, let's say we look at W2Q. So this is the second head, the weight matrix for it. It's 768 by 64. And it's going to get multiplied by your embeddings matrix, right? Remember your embeddings matrix was what dimension? 768 by 2. Actually, it was 2 by 768 because 2 rows and 768 columns. So one thumb rule for multiplying matrices is the inner dimension should match. If I say, oh, it's 768 by 2 times 768 by something, that doesn't match. So it's the inner dimensions match, you can multiply matrices. So 2 by 768 can multiply 768 by 64 because the inner dimensions match. Okay. So this will give me a matrix of size. Let's say this is Q2, 2 by 64, right? So this is for head number 2. Head number 1, head number 3, head number 12 will all have their individual query matrices, right? And they'll all have their individual key matrices. They'll all have their individual value matrices. So this is the first thing that you get. These weight matrices are learned as part of training. The Q matrices are based on the input. Q, K, V are input dependent. The weight matrices are input independent, right? You already learned them, it's fixed. It's just the Q, K, V that changes. The W's stay the same for every single head, right, when you do inference. Okay. So let's say, I mean, this is another, I found this to be an interesting way to visualize. So if I want to understand, so let's say this is, token 1, and then this is token 2, and this is token 3. And this is for a given head, okay? Let's say we fix the head. We're not looking across heads, fix a head. Within a head, you compare, right? You compare the tokens. So let's say I want to understand how much does token 2 and token 3 contribute to token 1, okay? This is my question. How do token 1 and token 2 and token 3 inform token 1? How do I understand the self-attention relationship between these tokens? I take the query vector for token 1, and then I look at the key vector for token 2, right? And then I can basically do a dot product, and I can understand the contribution. Or let's say I want to understand how token 1 informs token 2, then I take the key vector, query vector here, key vector here, right? So this is a contribution of token 2 to token 1, right? And then I kind of get a value here, and I normalize it, and then I multiply it with V. So I essentially multiply everything with query 1 with key 2, key 3, and key 1. And this gives me the weighting of every token for token 1, right? And then I sum it up, and that gives me how token 1 is connected to token 2 and token 3. And itself as well. So you do self-attention too. So how does token 1 connect to token 1? And then you also do it with token 2 and token 3. So you repeat the same with token 2 and token 3, right? Yeah. So we are actually, we're looking actually at token 1's relationship with token 2 and token 3. So that's what this graph represents. Because you pass in query 1 to token 1, token 2, and token 3. And then the respective keys get passed in there. You do a dot product. It's essentially a dot product. If you remember, we look at dot products. We discussed this last time. What's one intuitive understanding of a dot product in the embedding space? What does it tell us? Orthogonality, yes, cosine, but what is the concept there? Similarity. So the higher the dot product, the more similar vectors are, right? So here, the other intuitive understanding or concept here is attention. So the higher the dot product, the more attention you want to pay to that token and say that that token is more connected to me, right? So we saw dot product as a way to measure similarity. Here, dot product is a way to understand attention. So you can also view it as an attention mechanism. So if I look at Q1 dot K2, if this is higher than Q1 dot K3, it tells me that token 2 is more important to token 1 than token 3 for its own understanding and representation, right? So we're using dot products to convey attention or capture attention. Okay.
Can you repeat the calculation? So the QI is.
Yeah. So here let's look at this. So B1, we'll actually look at the math here. So B1 is Q1 dot K1 times V1 plus Q1 dot K2 times V2 plus Q1 dot K3 times V3. It's roughly that. We also normalize and do other things. I'm just skipping that, right? But essentially you're saying, I have values for every token, which I've also, done the multiplication, I've learned it. But I want to understand the token 1's attention so I'm communicating the understanding, right? So the new communicated understanding for token 1 is a combination of how much emphasis I need to place on token 1 plus how much emphasis I need to place on token 2 plus how much on token 3, right? So these are captured by these dot products. So this graph is essentially doing that.
And B1 is
B1 is like the new understanding of token 1 from the input embedding post the attention, right? There was already an existing understanding. I'm like, okay, this is who I am. But in context with other tokens, I've upgraded my understanding, right? I have gotten that communication from other tokens, and I've upgraded my understanding, and I'm representing myself in a new way. So that's what B1 is. And I do the same for other tokens as well. Okay. So if you have n tokens, then self-attention is, to do self-attention, what's the computational complexity? Not n to the power n. That's a lot. N cube. So we need to do n square computations, and each computation is, so you need to take, so for every query I take how many dot products? N dot products, right? And so there are n square dot products times the dimension of the embedding, right? In this case it's 64. So 64 times n square is the flops, number of flops. So that's why the self-attention mechanism is one of the more computationally intensive component of any given transformer block. And people also try to optimize this, right? Yeah, that makes sense. So like we said, it's not just dot product. You also have to normalize it. So there's a normalization. So it's called scaled dot product attention. Use of dot product for attention. Also scale it by the square root of the dimension of the embedding, which is 64. Square root of 64 is 8, right? So you can also think of it this way. Now that we have done all of this QK transpose business, we have understood how thinking is related to thinking, how thinking is related to machines, how machines is related to thinking, and how machines are related to machines, right? Now if you had like many more tokens, it's like a n by n matrix. So this attention is a n by n matrix where n is the number of, yeah, so A is an n by n matrix where n is number of tokens. Okay. So by having done all of this, we have understood how each token connects to every other token through an attention matrix, right? But this still doesn't give me kind of a probabilistic understanding. These numbers are not probabilistic. So people apply a softmax on this. So you can convert it into a probability vector between 0 and 1. So for every token, I can probabilistically say, I want to put 80% emphasis on this token, and all the other tokens combined only take 20%, right? Or I'm giving equal emphasis on every single token, right? So that is a probability distribution. So to do that, we need to apply softmax, okay? This attention matrix is not normalized. Once you exponentiate it and normalize it by the sum of exponentiations, you get a probability, right? So just take every element here, exponentiate, and divide it by the sum of the exponentiated quantity. So that gives you a softmax, and each row sums to 1. So let's say this is an alpha matrix. Each of this is a probability vector. So this is probability vector for token 1. For token 2, you get a probability vector, and so on. Okay. So the probability vector for token 1 tells you how much emphasis am I placing on any other token in relation to myself, right? So that's a self-referential attention mechanism is now captured in this probability vector. The only thing is this probability vector is like anything between 0 and 1. It's just the emphasis. The actual embedding is captured in the V, right? The A is capturing the emphasis, the V is capturing the representation. Now I need to combine the emphasis with the representation, okay? And that gives us the next step where we multiply alpha with V. When you multiply the alpha with V, you're now combining the emphasis, placing the emphasis on different vectors and combining them. So as an example, let's say I want to understand the weighted sum of values. So this is the B1 that we looked at, right? So this is a blend. let's say they look at the blend vector for token 1. So the blend vector for token 1 is alpha 1, 1, v1 plus alpha 1, 2, v2, so on, alpha 1, n, vn, right? In terms of a matrix, this is, let's see. Oh yeah, I think we are looking at a row vector. Okay. Yeah, so if we have v1, v2, vn stacked like this, and then this is alpha 1, 1, alpha 1, 2, so on, alpha 1, n. So we are looking at the first row of this matrix and multiply with the whole V matrix. And the V matrix itself has, each row is the value embedding for a given token, right? So this is the emphasis attention matrix. And this is the new embedding matrix, right? Because if you look at V as well,
Matrix is again row or is it column?
so here V's are represented as rows, V1, V2, V3.
But then if you, when you do the multiplication,
You can multiply it with a row matrix, row vector, no problem. So your B1 will be a row vector. Okay. Yeah.
the dot product,
Yeah, so the dot product will be, so dot product is actually between the alpha vector, alpha 1 vector. So this is actually not the dot product we are looking at, because now we are, let me just look at it. This is not a vector dot product. This is actually a matrix vector multiplication, right? So we are actually multiplying alpha 1 transpose with the V matrix. Okay. The dot product was already taken care of in the attention. We already did the dot product there. This is now combining the scaling all the value vectors for each tokens by the appropriate emphasis we already computed in the attention. So this is a vector matrix multiplication. So this gives you a row vector. Okay. Yeah.
How are the query and key and value, like values learned?
So that's everything's part of the training. You said, so what is part of the training? What is part of the training is the initial token embeddings, the position embeddings, the weight matrices for query key value for every single head in every single layer, unless the layers are identical. If the layers are identical, then you just repeat it. You don't have to learn it for every layer. So these are, you decided ahead of time that I don't know what these numbers are, but the data is going to reveal to me through my learning objectives, training objectives, what these matrices and the initial position and token embeddings should be, right? So these are your parameters for your model, essentially.
So, but if we're like, let's say, because you have the operations for the key, the query, and value, and they're
Mhm.
all applied together, how does it know which is which, as opposed to just taking the knowledge that each provides and just combining them together?
Yeah. So, I mean, you have to look at it in terms of training examples. So let's say I want to predict the next token, right? My output is going to be like forcing the model to predict that token, right? So I have to learn the weights in a way that the next token is favored over other tokens. So and I have to do it over millions of examples. Over millions of examples, I keep favoring certain tokens for a particular sequence of words. Then the weights have to be, set accordingly, right? And that happens through gradient descent. And you have a loss function, you optimize for it, you do gradient descent. And to begin with, you don't know what the weights are, so you set it randomly, if that's your question. At the beginning, everything's random, and then the randomness starts to become more and more deterministic as you go through the training. In the beginning, you have no idea what the weights are. At the beginning of any training, the model has no idea, so the loss can be very high. But as it goes through data, it's like, oh, I need to tune the weights here. The gradient is telling me to do that so that I can predict better and reduce the loss. So I want to reduce the loss, so the weights can start to get shaped up. Okay, so that's part of the learning. Okay, so weighted sum of values. For thinking machines, thinking becomes a contextual blend of thinking and machines because of this attention mechanism. In the beginning, thinking didn't know what, I mean, thinking had an idea of its position, that's it. It didn't know that there was something called machines. But with attention, thinking says, oh, well, I'm not just thinking, I'm also thinking machines. There has to be some component of that in my embedding. So that's what's happened after going through attention. And the same for machines. Machines are saying it's not some random machine, we are looking at a thinking machine. So there's some of that captured in the machine as well. Okay. All right, so let's look at an in-class exercise and then we'll take a short break. So assume that this is your value vector, right? Value vector for token 1 is this, and value vector for token 2 is this, and your attention looks like this. So this, all of this you can say this is alpha 1 1, alpha 1 2, alpha 2 1, alpha 2 2. Okay, this is your normalized attention, right? Where each of these sum up to 1. Okay, right? So you can see 0.7 plus 0.3 is 1, 0.4 plus 0.6 is 1. So now we have a probability vector for every token. So the question is, what is the transform token embedding for the token thinking? Or you can say this is a blended token embedding. What's a blended token embedding for thinking once you've done all of this, right? So just take a minute. So we'll take a 5-minute break. Yeah, take a 5-minute break and come back. Okay guys, so we'll just go through a quick understanding of heads through something that it's already loaded up, and then we'll switch to presentations in 5 minutes. So, we were talking about BERT model, and it has 12 heads, and we said different heads can take on different roles. So this is like a tutorial that I picked up from the web. It's called BERTwist tutorial, and I think there's GitHub for it, and it's linked on the course page as well. So you can take a look for the last lecture. It's one of the demos that I've linked it. So let's say there was a sentence, the cat sat on the mat, and the next sentence, cat lay on the rug. Two sentences that are passed as input, and they'll have separator tokens and start tokens and everything like we discussed. So one separator token and two separator tokens and one CLS token, the beginning, right? And then we have encoding of these as well. So all of that is done. And then this is, the different layers, and you can visualize across layers. But I just want to focus on layer 0 and look at different heads. So that's this one. And we're looking at BERT base uncase. So it's a base model. Like we said, 12 heads and 12 layers. So now we'll just fix a layer. We'll not go through other layers, but we want to go across heads. So like we said, there are 0 through 12 heads. So I was just playing around with it and seeing what is it. So like we said, you infer what is the head doing based on the relationships it has and how much attention it's paying. So these are the attention, the thicker the line, the more attention is being paid, between the two words. And this is, this has all, I think this is like self-attention within sentences, and we also have sentence A, sentence B. So you also have those attention. So this is sentence A, and this is sentence B, and then you have attention between sentence A, and you also have attention between sentence A and sentence B. So that's, but you can look at it, all of this as one sentence. That's also fine, because you can have attention go all the way from start to finish. So head number 10 is just looking at the next word. The cat sat on the mat. It's just understanding who's my next word. It's capturing information about the next word. Because sometimes when you try to understand a sentence, you need to know what's coming next. So I am just capturing my understanding of the next word. That's all this is doing, right? It's just saying this is the next, what's my relation to words next to me, right? Let's look at a different head. Head number is the one, I think it was head number 0 or 1. Let's look at 2. All right, this is yeah, this is also layer 0, so the patterns are still being learned. Let's look at a different one. Yeah, so here, so if you look at rug, it's connected to sat. You can sit on the rug. So, and it's not the next word, but there is a connection between sitting or laying and a rug. So you do an action on a particular object. So you can sit on the rug, right? So this is capturing, so this is paying attention. Rug is paying attention to sat. It's also paying attention to itself, right? So there's self-reference and also a reference to another word. Let's see if that's capturing other actions as well. Lay is connected to, so lay and sat are also connected here, which is interesting because they are two different actions that you can say is I lay down or I also sat down. But I don't know why it didn't connect lay to cat, just like it did with the rug. So this is a different head. We're still in layer 0, so it's still learning stuff. But you can see that this head looks so different from the other head we looked at, which is just looking at the next word. Here's an example, just a simple example of how you infer what a head is doing by actually looking at the attention it's paying to other words and then saying, oh, this is what you must be doing. This is what you're trying to capture, right? And so different heads are capturing different things. You can also play around with it and see what other heads are doing here. It may or may not fully make sense because we're still in layer 0. So you have to go to other layers and then take a look. But then when you go to other layers, the understanding has changed, right? Now you're looking at some other representation of cat or whatever. So it's a mixed representation. So you might have non-intuitive connections come up in forward layers. So that's why it's kind of a little bit harder to understand sometimes what's happening. But you can have a higher level understanding that, yes, heads are doing different things. And you can try to visualize to some extent, right? So that's an example there. So we'll go more into, all right, so let me just